Development Division of the National Severe Storms Laboratory. Prior to this, he worked in a variety of positions, including nearly 20 years at the National Weather Service Forecast Office in Jackson, Mississippi, including meteorologist in charge from 2002 to 2015. He was also a forecaster in Cleveland, Ohio, and started his NWS career at the now-defunct office, an NWS office in Columbus. Before working for the NWS, he worked in the weather department at KTVI-TV in St. Louis, Missouri from 1989 to 1990. Alan holds a bachelor's degree of science in meteorology from St. Louis University and a master's of science degree in emergency management from Millersview University. And it's my honor to introduce Alan Gerard to the stage.
Good morning, everybody. I appreciate the invitation from the Meteorology Club. As you heard in my introduction, I actually started my career here in Ohio back before some people in this room were born, I'm sure. It's great to be back in the Columbus area. It's been, I've been back once or twice since, but this is the longest I've been here, and I'm lucky to be accompanied this time by my wife, Lisa, who actually also started her career here in the Columbus area. She was a special education teacher for a number of years and started her career here at Hannah Lincoln High School before she followed me around the country for all the various jobs you heard, and for our 20 years in Mississippi. And it's great being back here with her, and being here to speak to all of you this morning. I think this talk will really blend in nicely from the speakers we heard this morning, from Seth and Mark's talks, because they actually brought up a lot of the challenges we have today with severe convection and flash flood warnings. And I'm going to spend the first part of my talk talking about a new paradigm that's being developed at the National Severe Storms Lab, facets. Better watch out, this thing rolls. To talk about some of the ways in which we're trying to develop a new system that will hopefully take care of some of these issues that you heard Seth and Mark talk about today. And then at the end, I'm just going to spend a few minutes talking about the defunct WSO Columbus, Ohio. I have a few pictures to share, and a couple of stories just to give some perspective, especially for the students here, of what the Weather Service was like 25 years ago when we had an office here in Columbus. All right, so you heard Seth mention facets this morning during his talk, and I'm going to spend a few slides here talking about what facets is. Facets is an acronym that stands for Forecasting a Continuum of Environmental Threats. And basically, facets really got its start at NSSL looking at the severe convection and flash flood warning programs. And it's really, if you really look at the way the warning program has evolved over the last half century in the Weather Service, really at its core it hasn't changed a whole lot. You know, Seth talked about impact-based warnings, and we now do polygon warnings versus just the county warnings that we did 25 years ago. But at its core, it's still a teletype era product. The text nature of it, the deterministic nature of it, whether you're either in a warning or you're not in a warning, has not really changed since the warning program really took shape after the 1965 Palm Sunday tornado outbreak. Oops, sorry. So at its core, this reinvention has at its heart going from the polygon yes-no deterministic warning to a warning system that's based on gridded probabilities. In other words, some of you may be familiar, the Weather Service now produces forecasts in a graphical forecast editor that are grid-based. In other words, you get them through a graphical interface where it can be, the data can be parsed and viewed in many different ways using like GIS platforms. And basically we're talking about going to a warning system based on that sort of paradigm. And at its heart, it's about quantifying and communicating forecast uncertainty. Seth talked about the various challenges of trying to communicate the uncertainties associated with a tornado risk with a QLCS that may only produce 2 or 3 tornadoes along its path that are fairly short-lived, but obviously the people who are in particularly vulnerable situations, like people in mobile homes, they want to know about that 20 to 30% risk of a tornado and have an opportunity to take some sort of action. Whereas somebody that lives in a 3-story home with a safe room in the middle of it may not want to take action until it gets to a significant probability for a stronger tornado. So that's the kind of stuff we're looking at trying to do with facets. So again, at its heart, facets is meant to be a continuous stream of high-resolution probabilistic hazard information extending from days out, like the outlook phase that SPC does now, 7 to 8 days out, all the way into the warning time space, where you're talking about the next 15 to 30 minutes, and trying to construct a paradigm where we can provide a continuous flow of information that's probabilistic in nature, that's gridded so that users can ingest it and use it in various different ways, and do it for that entire time and space scale. So this little animation here just gives you an idea of how this might work. This is how SPC does things today with slight and moderate risks. Only, the focus would be on the probabilistic nature of this, and then for the warning phase, you would have some sort of blend of automated probabilistic guidance and that the human forecaster could go in and adjust on the fly to generate these swaths of probabilities. Those of you who are familiar with Hurricane Center products are familiar with probably the strike probability graphics that they've been producing for a number of years. And this is basically trying to take that concept down to the severe thunderstorm and flash flood warning scale. So why do we want to do this? And as I said, we already had some pretty good discussion on this morning in Seth and Mark's talks, but I'm going to go into a little more detail on this, and I've kind of alluded to this, but I just want to go into a little more detail. Warning polygons have a tendency to be very messy. Seth showed his his kind of mock scenario of how many tornado warnings you would need along a QLCS to cover all the various little mesovortex signatures developing along it. This is an example here from a very recent case. This is from a severe weather episode that went through the Kansas City area just a couple of weeks back, and I just want to, preface this by saying I'm not trying to throw any particular forecast office under the bus by showing their graphic. This is about the system. The system is just inherently challenging to try to generate polygons when you have one of these events like this, which is kind of a hybrid between a QLCS, and you have supercells out ahead of the line, and you have supercells embedded within the line, and you have mesovortices spinning up within the QLCS. It really gets messy in a hurry. And part of the reason why it gets so messy is forecasters are trying to do all of this manually. They're trying to generate all these products just based on their interpretation of the radar. And Seth alluded to a lot of the work we're doing with facets is not only in this conceptual framework, but also trying to develop the tools to blend all of this massive amount of data that's coming into the forecaster. And we're not, Seth hit on radar data. He didn't even go into GO 16, which is going to provide a whole additional fire hose of data that a warning forecaster has not really had to look at in the past. Really, radar was our meat and potatoes when it came to severe thunderstorm and tornado warnings. GO 16 is going to be providing higher temporal and spatial resolution satellite data that's going to enable it to be integrated a lot more into the warning space. And we're going to need tools to integrate that data, so we don't expect the forecasters to sit there and wade through hundreds of products in a matter of a couple of minutes. So another challenge with this is it's inherently binary. You're either in a warning or you're not in a warning. There is no gray area. So even if you're not really in the path of the mesocyclone, if you're in that polygon, and Seth alluded to nursing homes and various vulnerable populations, they're taking action. They're not looking to see, well, they hear the warning and they take action. We feel like in a paradigm like facets, we can start to narrow down the risks a little bit to really get to the core of what the risk for not only tornadoes is, but what the probabilistic risk for large hail, damaging winds, lightning, and flash flooding is. And then Seth again alluded to this, a great segue, the large false alarm area that you have. This is a graphic that we got from Patrick Marsh, who's now the WCM at the Storm Prediction Center. And this is just a representation of the area in red represents the entire area that was in polygon tornado warnings for the period from 2008 to 2012, the 5-year period. The area in yellow is the area that actually was impacted by tornadoes during that same time frame. So it gives you an idea of the large amount of area we're warning to try to capture that small amount that actually gets impacted. And then again, the teletype era, I won't go into too much more detail on this, other than just to say that this warning here that I have up is an example of an actual warning from the February Delta tornado outbreak of 1971 in the lower Mississippi Valley. I reformatted it to put it in the bullet format we use today, but we do impact-based warnings now, so the format has changed a little bit, but this is still basically, if I put that warning in front of most people today, they wouldn't think it was anything unusual, and it's actually a 50-year-old warning. So it just gives you an idea of how far we've come and how far we've not come. So again, to go into why facets, this is some of the tools that I mentioned that we're developing at the Severe Storms Lab to try to help the forecasters better be able to provide warning information. The graphics on the left are from Warn on Forecast. This is some of the initial guidance that's being generated from very high resolution computer models that are meant to actually provide the forecaster with numerical model output on the warning scale, basically trying to show where we may have tornadic storms, hail-producing storms, and flash flood-producing storms in the next 0 to 3 hours. And that's really a paradigm change for forecasters. They're not really used to looking at model data to help make warning decisions. I mean, we look at model data to help know what the environment is that the storms are occurring in to help with the warning decision process, but this is actually trying to get to that next step where you may not even have a storm yet, but you're starting to generate warning information because you have confidence that a storm is going to evolve with a combination of this kind of model data, satellite data, radar data. And then on the right is from a product called Prop Severe, which I'm sure a lot of the Weather Service people in here are familiar with. This is one of these new data fusion products where you're basically taking radar data from MRMS, satellite data, and lightning data, and integrating it through machine learning to generate probabilistic guidance for a storm to produce severe weather in the next 60 minutes. We've been testing this out in the hazardous weather test bed for the last few years. I know a lot of forecasters have been ingesting this. Our forecast offices have been getting this information into their offices to help support warning operations. And this is just an example of showing how we're getting this information, and the scientists at NSSL have started utilizing it to generate these plumes to show where a probabilistic hazard information warning might look like in a facets-based environment. So this graphic here, you see the actual warning that was generated for this storm, and then an example of what a fee-based probabilistic plume might look like generated from prop severe. And this year in the hazardous weather test bed, we're actually going to be doing some of the first testing of prop Tor, which is basically taking this to the next level, but generating probabilities of a tornado in the next 60 minutes. And this tool was generated primarily by the folks up at University of Wisconsin who have been working with these data fusion techniques. So again, why do we want to do this? This is just a real quick example to show the differences in vulnerability. This picture on the left here is from a Boy Scout camp in, I believe it was western Iowa, that was impacted by a tornado a few years ago. And this example is an igloo-shaped concrete home that was impacted by a tornado in the last few years. The people that were in this location out in a Cub Scout camp in a very rural area are in a much more vulnerable situation than somebody who lives in a concrete dome home. It's just a very different vulnerability. They may not want to, they need to take action very early. As soon as there's some risk of a tornadic storm. This person may not need to take action until the tornado is right on top of them and they just need to move into some sort of safe room in the interior of their home. Very different vulnerabilities, but right now we're providing them all with basically the same tornado warning. And then I want to make sure that I don't leave you all with the idea that this is strictly about severe thunderstorms and tornadoes. Facets is meant to get to this idea of providing probabilistic information for all aspects. At NSSL, we're focusing on severe weather and flash flooding, but other parts of the Weather Service and NOAA are looking at tropical weather, winter weather. And I just want to give an example. There was a winter storm in early January that impacted the southeast, and this is just an example of a graphicast at the Atlanta office. Again, this is about the system, not about particular offices, but it's just for illustrative purposes. And you can see here in this graphicast, they tried to convey some confidence and probabilistic information in a very generic sense. But the headline is, it's going to snow. And then in here they talk about some of the confidence issues, and then in here this is actually the winter storm warnings that were in effect. But then when you go to what actually happened, there really wasn't much snow when it all came to pass. It ended up being primarily an ice event for the Atlanta metro area with some limited snow accumulations up in far north Georgia. Well, as you might guess, the public wasn't real amused by this. And I pulled these Facebook comments. This actually isn't from the Weather Service Facebook. This is from one of the TV stations in Atlanta. But you can see a lot of comments about crying wolf and people aren't going to pay attention. You told us we were going to have 4 to 7 inches of snow, blah, 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 blah. And the reality is we have all sorts of ensemble information and probabilistic information. The problem is we don't have an easy way to communicate and convey that to the public in a way that's understandable. And that's why we want to go to this, because I mean the reality is, as much as we as human beings want yes or no answers, the atmosphere does not work like that. It works in a probabilistic framework. That's just reality. We are a long way from being able to provide deterministic yes-no answers for any type of weather phenomenon. But we want to be able to convey that probabilistic information in a way that makes sense to the variety of users that use weather information. Emergency managers have their own needs. Broadcasters have their own needs. The public has their own needs. And that's why we have social science really deeply embedded into this research to operations effort to try to ensure that what we end up generating in facets will be able to be utilized by all these different users. So I'm just going to touch on this real briefly because this is kind of more of the bureaucratic stuff, but it's just to really show that this is something that the Weather Service, NOAA, and the broader meteorological and water communities have been talking about for a number of years, that we need to start going to more of a probabilistic framework for our weather and water services. And we're really trying to develop facets to try to get to some of these, try to achieve some of these goals. So how are we doing this? At NSSL, basically when the facets concept came up, and again, we're focusing on the severe weather and flash flood aspect of this, we got together a number of people from across the meteorological and hydrologic communities, researchers, operational folks, weather service, broadcasters, private sector, and locked them in a room and said, okay, here's where we are today, this is where we want to be in facets, how do we get there? And they identified a plan that basically consisted of 46 various projects. Some of them are physical science research projects, some of them are IT type work, but as you can see, the biggest number of them are actually social and behavioral science, trying to figure out, okay, we're going to get this probabilistic information, how do we convey it in a way that makes sense to the public and other users? So the initial phase of this, we got 3 years of funding from NOAA's weather research program to do a project called Probability of What? And the reason why it's called that is because the first question, I'm going to go into this in a couple slides, is what are we trying to say the probability is? What is the definition of the probability for a tornado at the warning scale? I'll explain that a little more. There are many partners involved in this project: SPC, WPC, GSD, which is another entity of NOAA that does a lot of forecast model development and IT work. A number of universities, including OU, and then locally here to Ohio, the University of Akron has a social and industrial science engineering program, and they're working with us. So the goals of this project are to try to accelerate transition of facets to some sort of an operational capacity at the national centers, SPC and WPC, by the end of the project next year, and set the stage for FEE to be starting to get into the WFOs sometime in the next several years. That's very fluid. So these are the 11 multidisciplinary projects that we're working on as part of the Probability of What. You can see 4 of them are basically based on developing probabilistic guidance. 5 of them are developed on looking at the interfaces that forecasters are going to utilize to generate this kind of combination of algorithm and human-derived products. And then 2 of them are strictly end-user projects focused on social science and how the public and other users are going to interpret and utilize this new probabilistic hazard information. So I mentioned a couple slides ago that this project is called Probability of What, and this is the reason why. The first thing you really have to do is figure out, for those of you who are familiar with Storm Prediction Center, they've been doing probabilistic outlooks for a number of years. And they do probabilities based on the concept of having an event occur within 25 miles of a point. In other words, when you see on an SPC outlook a 30% probability for the day 2 outlook, that is basically telling you that there's a 30% probability that an incidence of severe weather will occur within 25 miles of your point. But utilizing that kind of a framework at the warning scale may not make sense like it does at the outlook scale. And it also might not make sense for an outlook that's generated for severe weather probability 10 days from now. So this initial sub-project of our project is basically trying to figure out what the right temporal and spatial resolution is for these various probabilities. And many of you are probably familiar with Dr. Harold Brooks, who works at the National Severe Storms Lab. He and one of his graduate students are who are focusing on this problem. And one of the things that they've done in their initial work is they've determined that on a given day, the overwhelming majority of severe weather reports occur in that 25-mile radius within a 4-hour window. So in other words, if you can figure out what that 4-hour window is going to be, you can encompass 95% of the reports that are going to occur in a given area on that day. So as SPC is trying to develop higher temporal resolution outlooks, they're focusing on this 4-hour window as their first effort. So they're going to be testing in the hazardous weather test bed this year, generating 4-hour outlooks. In other words, they're going to take the day one outlook they do today and break it up into 4-hour periods and try issuing frequently updated outlooks for 4-hour time frames. And then for guidance, there's another set of researchers and forecasters at SPC that are working on taking guidance from the SREF and the SSEO and generating 4-hour calibrated probabilistic guidance from those models for the forecasters to utilize as first guesses for their 4-hour outlooks. And if you look at that word calibrated, what we mean by that is that if we tell you that there's a 70% probability of an event occurring, that it happens 70% of the time. And same for 50 and the same for 30. So that's what we mean by calibrated. We want it to be robust in a way that that if a user wants to develop a cost-loss model where they say, well, I know that when the probability gets to 20%, that I'm actually going to get severe weather 20%, and that's the threshold at which I need to start taking action. So the key with this probabilistic guidance is developing it in a way so that it's calibrated. I want to talk a little bit about another experiment that we're doing as part of this FACETS effort, and that's the fee prototype experiment. And that's basically taking the guidance like you saw, the warn on forecast guidance, the prop severe guidance, giving that to the forecasters. They can ingest it with a prototype editing tool and then utilize different tools like what you see here is a way where the forecaster can edit the probability trend for a given storm over the next 60 minutes. They can go in and edit that. They can adjust the direction of motion and generate a fee forecast for the next 60 to 90 minutes. That's a blend of the guidance that they got from prop severe, warn on forecast, their own interpretation of the radar information, and very quickly generate a human value-added fee plume that can then be generated to users like emergency managers and broadcasters. And we actually have emergency managers and broadcasters that come in, get this information, and utilize it to try to do their jobs in a in a mock way. And then we have human factors experts like the folks from University of Akron, OU, social scientists, to evaluate how the forecasters are comprehending and generating fee, and then how the users are interpreting it and utilizing it in their jobs. And this just goes into that a little more detail. This is an example of the broadcast room of this experiment. This is, some of you may know Bob Ryan, who was a longtime broadcaster in the Washington, D.C. area. He was one of the broadcasters that came out to the hazardous weather test bed last year and actually worked like he was broadcasting a severe weather event. We actually recorded it using Google and fed it into the EM and forecaster rooms, so we were replicating that whole integrated warning team process that the Weather Service utilizes. And this again is just an example. This is from a real event that we worked in the hazardous weather test bed last year. This was a series of tornadoes that was produced by a single supercell in the Dodge City area back in late May of last year. And you can see this is an actual fee plume that one of the forecasters generated for this tornadic supercell. And then this is an example comparing the Weather Service polygon with the fee polygon, and that looks really good. But The challenge with this event was this single supercell was producing cyclic tornadoes. I mean, it was rapidly producing one tornado after another. You're very close to the radar. You can really see it well. So there's challenges there with the forecaster on how narrow. You know that 5 minutes later to the northwest, it may generate a new tornado. So those are the kind of challenges that we're trying to work through in the hazardous weather test bed. And then this is just an example of one of the user graphics that can be generated from FEE. This is kind of a combination of the FEE plume and some timing information. We really got a lot of feedback from the emergency managers, and I'm sure this probably doesn't come as a surprise to a lot of the people that work in the community, that timing was just about the most important information they needed. Like one of the emergency managers that was in with us last year was the emergency manager for the University of Oklahoma. And he has to make decisions about when to activate evacuation plans for dormitories. He has to make decisions about when he's going to call intramural sports and tell them to get off the field because of lightning and then get into a safe place. They really want that timing information. And we're just looking at different ways to provide that in a manner that really will be intuitive to the users and that they can utilize to make the best decisions. Again, this is just some results. The main reason I wanted to show this slide was just to emphasize that I think a lot of people think hazardous weather test bed, Norman, Oklahoma, you're looking at supercells. We are looking at supercells, but we're looking at a lot of other cases as well. Not only do we look at live weather that's going on while the test bed is in operation, we also look at archived cases that we play back through. One of the CAN cases that we used last year was a pulse lightning and microburst case from Georgia from the summer. We looked at a QLCS severe case from Vortex Southeast from Alabama and Mississippi. Some of our live weather cases included a Western Region supercell event, a tropical cyclone event in Florida, and a couple of Ohio Valley kind of hybrids, QLCS and supercell events. So we're really trying to put this through its paces through all of the various types of severe convection that can occur in the United States. So where do we go from here? We're currently in our second year of this probability of what grant. Harold and his team are continuing efforts at the definitions. We just started hazardous weather test bed operations for this spring. Week one we have the FEE prototype experiment that I went into a fair amount of detail, but we also have a FEE hazard services experiment, which is basically taking the prototype work and the folks from GSD out in Boulder and people at NSSL are putting it into hazard services, which is the next generation of warning preparation software that the Weather Service will be using in AWIPS. We're trying to expand our social science efforts. We have a new effort that's spinning up in Norman called the Alliance for I can't read it all. I'm not going to try. But it's basically an alliance that's going to be focused on nationwide efforts to try to bring more focus to social and behavioral sciences and integrate it with the physical science of meteorology and other environmental sciences. And this on the right is just an example of one of the OU social scientists, some of the work he's doing, where they're actually going back in and doing deep dive surveys after severe weather events to try to find out what the public gleaned from the information they were getting. And one of the findings they've determined is that about half of the people who report that they were in a severe thunderstorm or tornado warning based on their memory, when they go back and plot where they were not in a severe thunderstorm or tornado warning. And so we're trying to figure out why that is. Is it because they were in a flash flood warning and they just didn't understand? Or they heard the media just talking about severe thunderstorm and tornado warnings, so they just assumed they were in one. It speaks to, and I'm just going to speak for myself, as a meteorologist in the Weather Service for 25 years, you get focused on producing the forecast and warnings. It's very easy to forget that the people out there in the public have their own lives, they're doing their own things. They're not sitting there focused on the weather. So we need to understand what is the public getting out of the information that we're conveying to them. And then this facets expansion concept, I won't go into too much detail on this, but just to show that we're not just looking at this again for severe convection. We're trying to, at NSSL we've started with severe convection, but our intent is to leverage the lessons that we learned from that and take them to the next level with these other products. Am I over time, Matt? Oh, we're fine, okay. I just want to make sure. So I'm just going to take a few minutes. That covers the facet stuff. I just want to take a few minutes because I was asked to talk a little bit about my time at the WSO in Columbus. So real quick, for those of you, and especially for the Ohio State students, the weather service of today is not the weather service of 25 years ago. There used to be hundreds of offices around the country where we're big. Generally, this is not 100%, but generally speaking, each state had a forecast office that did the forecast for the entire state, and then there were smaller weather service offices that did local warnings and forecasts and took weather observations. And generally, those offices were staffed with meteorological technicians, which were usually people that had come from the military and had been trained as forecasters in the military but didn't have formal degrees, and med interns, people that were hired in at entry-level positions. And this is showing a map of John Glenn Columbus International Airport, which was not called John Glenn Columbus International Airport, then it was Port Columbus. And we were located across the runways from the terminal building. And this is, the building is still there. This is a Google map of the building as it exists today. Showing you this was the main WSO building. This was where we had our observing equipment. And this was the building for the WSR 74C, which was a conventional radar, which the tower was off over here. And we had 6 employees, 3 med techs and 3 interns, and a meteorologist in charge, an electronics technician who kept the radar and the IT equipment going. And this is the way the building looked 3 years ago, I think it was, when Ariel and I drove by it. And I just was going to show that I started in the Weather Service on September 10th, 1990, and 4 days later, we had this severe weather event, a September severe weather event in the Ohio Valley that actually produced an F2 tornado that moved into our service area down here around Washington Courthouse. This was the county warning area for the Columbus Weather Service office at that time. We went down to Athens, Chillicothe, Newark, up to Delaware, and then just basically these counties directly west of Franklin County. And we were one of a lot of offices in Ohio back then. All of these offices, Dayton had an office, Cincinnati, Huntington, West Virginia covered south central Ohio, Akron, Canton covered most of the eastern part of the state, except there was an office in Youngstown. The Cleveland FO also covered, had a number of counties for warning responsibility, Toledo, and then Fort Wayne covered these counties in far northwest Ohio. And I will just say, I did that from memory, so Ken's in the office here. I may not have that 100% right, but I think I'm pretty close. And just to tell you how different it was, Dayton, Mansfield, Toledo, Youngstown, and Huntington did not even have radars. They were expected to generate warnings based on looking at a monitor of a feed from an adjacent radar or getting a phone call from an office that had a radar telling them they needed to issue a warning. That was it. I mean, I used to call Dayton all the time and say, hey, you got a storm with VIP 5 to 35,000 feet up over Auglaize County. I think you might want to do something about that. I mean, that was the way it worked. I often tell people, I'm amazed we didn't kill more people than that. I mean, it was a totally different, and I say that, I was part of it. We did the best we could, but when you compare the National Weather Service of the 80s and 90s, I'm sure it was a way more modern and better than it was in the 60s and 70s, but we've come a long way. So facets is the next step, but we're a lot better off than we were in 1992. This is an example of yours truly in the weather radio room at the Weather Service office in Columbus, recording the local forecast for Columbus and Central Ohio. And this is me working the 74C. That was not me actually working the 74C because we did that in the dark. You turned the lights off, you put an overlay over it, you got colored pencils, and you drew over on the overlay where the storms were, and then you walked back out and you typed up a warning. So that was back in the day. I'll just touch real quick. The two biggest weather events that occurred while I was here was the November 1992 tornado event, which was really more of a Cincinnati event than it was a Columbus event, but I was just going to point out that these are the storm reports from this event in Ohio, and you can see there's nothing down here in Ross County. And I remember vividly that we had a supercell that came up through south central Ohio and produced baseball-sized hail near south of Chillicothe. Didn't even get reported in storm data. I was able to go back and find there was a warning issued for Ross County, so I'm not losing my mind. There was a supercell there, but we were not as good at documenting severe reports back then as we are today. And then the storm of the century was the other one, and I know I got to be running out of time, so I'm just going to pop through this real quick and just say, for those of you that may have been around here, some of you folks more my age, we were on the edge of the 93 storm of the century, but I had the joy of working the evening shift that night, which was the peak of the storm for central Ohio. We only got about 5 inches of snow, but it was 5 inches of snow driven by 35 to 40 mile an hour winds. And what I will never forget is trying to take out the snow observations in the front yard of the WSO and trying to average bare ground and 20-inch drifts, because that was the way the snow had ended up getting laid out. So it was a different era. It was a fun era. I loved my time here in Columbus, and I'm done. So thank you.
Thanks so much, Mr. Gerard. Unfortunately, we don't have